The Chinese Postman problem. One walk through town that covers every street as short as possible. To solve it, we will snap together 3 tools from our earlier videos. Here's a small town. Mailboxes line every street, and each one needs today's mail. Each morning, the postman leaves the post office, walks through the town, and returns home. To deliver everything, every single street must be walked at least once. The question is in what order, so that the total walk is as short as possible. As always, we first turn the map into a graph. Each intersection becomes a vertex, and each street becomes an edge. The post office sits at vertex D. Every street also carries a length. Walking a street costs its length every time we walk it. So the task is, find a shortest closed walk that uses every edge at least once. The problem was posed by Mei-Ko Kwan in 1962, hence the name. It is also known as route inspection. One observation before we start. If no street ever had to be repeated, the perfect route would be an Euler circuit. That is worth recalling. From the previous video, a connected graph has an Euler circuit, a closed walk using every edge exactly once, precisely when every vertex has even degree. In this little town, every degree is even, so an Euler circuit exists. The postman simply walks it, covering each street exactly once, 14 in total. And nothing can beat that, because every street has to be paid for at least once. So whenever all degrees are even, the Euler circuit is the optimal route. And we are done. Back to our town. Count the streets meeting at each vertex, its degree. 4 vertices, B, D, F, and H, have odd degree 3. But an Euler circuit forces every degree to be even. So this town has no Euler circuit. The postman must repeat some street. The question is which ones. Here's the key idea. Suppose the postman walks street BE twice during his round. Picture that second pass as a duplicate copy of the street. The walk then uses every copy exactly once. Duplicates change degrees, and they change them at both ends. B is repaired, but E, which was fine, is now broken. Duplicate the next street as well. E is flipped a second time, back to even, and H is repaired too. So a duplicated path repairs exactly its 2 endpoints. Every vertex in the middle survives. That turns the whole problem into a clean question. Choose duplicate copies of minimum total length so that every degree becomes even. Then an Euler circuit of the doubled town is the postman's route. Of course, D and F are still odd, and we never checked whether this repair was the cheapest one. So let us rewind. From last time, we know the number of odd vertices is always even, so they can be paired up, and each pair joined by a duplicated path. To pay as little as possible, each pair should be joined along a shortest path. Suddenly, this is a shortest path problem. Shortest paths are Dijkstra's territory. His algorithm finds shortest paths from one vertex to all others by always settling the closest unsettled vertex. See our Dijkstra video for the full story. Here we need the shortest distances between the 4 odd vertices. For example, from B to D, the cheapest route does not use the center. It goes around the corner, 2 plus 1, total 3. Running Dijkstra from each odd vertex fills in all 6 pair distances. Now forget the streets for a moment, and picture just the 4 odd vertices joined by these 6 numbers. In this little helper graph, each edge is one possible pair, weighted by its repair cost. Pairing up the vertices means choosing edges so that each vertex lies in exactly one pair. In other words, a perfect matching. With 4 vertices, there are only 3 perfect matchings, so we can simply compare their costs. The cheapest one pairs B with D and F with H at a total extra cost of 8. With many odd vertices, this step becomes a minimum weight perfect matching, solved by a weighted version of Edmonds' Blossom algorithm. Our video on the Blossom algorithm covers the maximum matching case. Time to build the root. We duplicate the matched shortest paths. The first pair is joined along BAD at extra cost 3. The second pair is joined along FIH at extra cost 5. Every degree is even now, so the doubled town has an Euler circuit. Heyerholzer's algorithm from the previous video hands it to us. Watch the postman walk it, starting and ending at the post office. Duplicated streets are walked twice, once along each copy. $33 for the streets, plus 8 for the cheapest repair of the odd vertices, and no route can do better. The optimal postman tour has length 41. Here is the complete algorithm. Find the odd degree vertices. Compute shortest paths between them with Dijkstra. Find the cheapest perfect pairing with matching. Duplicate the matched paths. And output an Euler circuit of the doubled graph with Heyerholzer's algorithm. Every step runs in polynomial time, about n cubed overall. 3 of our earlier videos snapped together. 3 neighbors of this problem are worth knowing. If every street is one way, the postman problem is still solvable in polynomial time. Mix one-way and two-way streets, and it suddenly becomes NP hard. And the famous cousin, visiting every vertex once instead, the traveling salesman problem, is NP hard as well. Covering every street is easy. Visiting every vertex is hard. Thanks for watching. If you enjoyed this video, please like and subscribe to support the channel. More graph theory videos are coming soon.